first. Just give me a second here. All right. Looking for something here. All right. Here we go. This is what I want. All right. So again, good morning. And what is the schedule for today? We'll be doing a review for our final test, test number 3, which will be this coming Thursday. And let me tell you what test number 3 will, what chapters in the book are covered, and also, obviously, we're going to be doing stack key also in this test. But let me see, if you have a pencil, you should write this down, what the chapters are. Just give me a second here. All right, so for this test, we will have chapters 14, 16, 17, and 19. In addition, I would recommend reading, if you've not already read these sections. Now, I haven't posted
I'm sorry, Professor. Can you repeat that? I'm sorry.
14, 16, 17, and 19. In addition, the sections that you need to also read, which would be helpful to read, which deal with confidence intervals and hypothesis tests, are sections 20.1, 20.2, that's in chapter 20, just those 2 sections, don't read any more. And then in chapter 22, read sections 1, 2, and 4, nothing else. Not posting these because the book's PowerPoints are for the entire chapter, and I don't want you reading more than that. So please, there won't be PowerPoints for those. Again, chapter 20, sections 1 and 2, and chapter 22, sections 1, 2, and 4. All right. In addition, of course, you need to know how to do or interpret stack key bootstrap confidence intervals and stack key randomization hypothesis tests. All right. It's like we've been doing the last 2 weeks. All right. So that's what's being covered in this test. So we haven't, covered these earlier chapters recently, 14, 16, 17, and 19. So I'm going to spend a little bit of time during the review going over those. All right. Now, I'm not sharing the screen with you because I am currently looking at your test. So obviously, I'm not sharing that with you. But I do want to go over the types of questions that you should be looking for. Know the difference in this test between personal probability and what they call relative frequency probability. Now, will it be a definition? No, not necessarily a definition, but there'll be a scenario. There'll be something that I will tell you about, and that you'll have to think about whether it's personal probability or relative frequency probability. A personal belief probability would be one where you're just guessing at it, right? You may be using your own experience, but it's not going to be an exact probability, right? Yes, 2 people, the question, what's the probability it will rain today, later today? All of you will give different answers, all right? So it's not something that, it's a personal belief. On the other hand, if we played a game with playing cards, like poker or some other card game, we can quantify the probability of you getting a certain hand. That is an exact quantification of probability. Make sense? You can do that ahead of time, right? That's why people bet in poker, if you've ever played poker. And that's why some hands are better than other hands, because they have lower probabilities of occurring. A winning hand is a lower probability hand. So that's how, but it could be quantified ahead of time. On the other hand, probability that it will rain today or tomorrow cannot be quantified exactly, right? Makes sense, right? This is common sense I'm talking about. Also know that if you repeat, if you do a probability experiment in the sense of a relative frequency approach, where you're repeating an experiment over and over again and recording your results, know that many probability experiments, one trial of that experiment, one time that you do it, is typically independent of another time that you do it. For example, if you were flipping a coin, or if you were playing the lottery, each time that you would do it, the probability would be independent of how you did before. For example, you might say, all right, I just flipped the coin 8 times and I got 8 tails. And those people in the world would say, oh, that means it's a much higher probability that you're going to get heads on your 9th flip of the coin. No. The 9th flip of the coin has nothing to do with what occurred before. It doesn't matter what the other flips of the coin did. If they were all heads, it doesn't matter. The 9th flip of the coin will still be 1/2 probability of heads or tails. That's called independence. So typically, not all situations, but typically, when we repeat a probability experiment, one trial will be independent of another trial. Okay, does that make sense? So that's something you should obviously know. That's one of the takeaways from chapter 14. Okay, and again, know the difference between personal probability and relative frequency probability. Okay. Know that if you have 2 different types of events that are occurring either simultaneously or consecutively, and they're independent of one another, and you know the probabilities of each one of those, probability that they both occur is the product. You multiply their probabilities. Okay. So for example, if you flip a coin, and let's suppose you have a wheel that has 10 equal pieces to it, a wheel, one of these wheels that you would see in a casino or something, and they have 1 to 10 equal numbers that could occur if you spin it. You might say, what's the probability of getting heads and getting an even number on the wheel? Well, how many even numbers are there from 1 to 10? Well, there's 2, 4, 6, and 8. There's 4 even numbers. So the probability of getting even numbers, 4 out of 10. Probability of flipping heads is 1/2. So 1/2 times 4 divided by 10. All right, if you multiply those 2 numbers, those 2 fractions, that would be the probability of getting heads when you flip the coin and getting an even number if you spun the wheel. You did both of those things, you multiply those 2 probabilities. Questions about that? And they're independent of one another, right? Flipping the coin and spinning the wheel, they don't influence each other. They're independent. They have nothing to do with each other. Also know the definition of expected value. Expected value, it's like an average, but if you're given a percentage or probability for each type of event, for example, if you were told that there was a 30% chance that you would win $100 and 20% chance that you would lose $50, okay, and you wanted to know the expected value of those 2 events, you would multiply the percentage or probability times its value for each one of those events and then add them up. And you would get the expected value. It's in your book, and they give examples there. Something you should know how to do with your calculator. Okay. You should know the difference in this chapter. Let me see what chapter this is. Let's take a quick look. Chapter 16, psychological influences on personal probability. They talk about these different types of things that affect your assessment of personal probability. Things like the certainty effect, the pseudo-certainty effect, the availability heuristic, anchoring, all these things that are mentioned in chapter 16. Read through it, make sure you understand what they referring to. Look at the examples, all right, because the examples are there to help you understand them. You don't have to memorize these things, but you have to know where they are in your book, so that when you see a question that deals with anything in chapter 16, you know where to look for it. Okay. Also, and this is something I hope you all know how to do, even with ebooks, they have an index at the end of the book, right? Index. And you just look at the index and look for that particular topic. It'll tell you what page number it's on, right? Now, when I was growing up, we didn't have ebooks, we had textbooks, and everybody, I'm literally telling you, everybody knew how to use an index. Now, we never had open book tests when I went to school. We had to memorize everything, literally everything, a lot more than what people are memorizing today. But we knew how to look things up on an index if we had to, right? For homework or whatever we would be using the book for. Since this is open book, you should know how to use an index. So you should practice that. Look at the index, find topics, things like that. Know how to maneuver inside your ebook if you have an ebook, or if you have the paperback version, know how to find things in your paperback. This is all common sense, right? I'm telling you, but you'd be surprised how many people don't know how to do these things.
Professor, real quick, our quiz today, the chapters is on what?
It's just hypothesis tests. Randomization hypothesis tests. Stat key. Okay. I did mention that last time. I mentioned that last time. Mentioned it.
Yeah, you probably did. I forgot. Okay.
That's okay. It's okay. But you need to write these things down and review before you come for the session, before you come for a quiz or test. That's the best thing to do. All right. Anyway, so there are a few questions that deal with this chapter 16 topics. All right. Again, read through it and look at each of the different types of psychological influences mentioned in chapter 16. And look at the example so that you get an idea of what these things are referring to. All right. This is a little complicated. Terms are, are not easy to understand, some of them, but if you read through the examples, they might help you get a better grasp of it. There seems to be a few questions, again, personal probability versus relative frequency probability. So make sure, again, you focus on that. Make sure you understand the difference between those two so you can answer some of these questions. Also, I'll give you a little bit of a hint. In one of these chapters, I don't know if it's chapter 16 or chapter 17. It's chapter 17. There's one question in here that has to do with the birthday question. Look at the birthday question on page 367. That's all I'm going to say about it. Give you a little hint. Make sure that you read through that and you know what information is there. Right? Again, that's all I'm going to say about that one. That'll be an easy question if you actually have read chapter 17. Make sure you know about the gambler's fallacy. Now, the gambler's fallacy is in chapter 17. That's an important topic I've covered. Make sure that you know the following information. The gambler's fallacy applies only to independent events. If events are dependent on one another, then it does not apply. All right, it mentions that here, but it's an important topic that might be in the test. So make sure that you understand that. Then I will mention very, very important topic, but it's one that could be tested on, I would say almost certain. And on page 373 in chapter 17, they talk about sensitivity of the test, specificity of the test. Make sure you tag that, know where it is in your book, an ebook, so that you can refer to it if in case they talk about it in the book. And also know the difference between the probability of false positives, probability of false negatives. Know what false positive is, know what a false negative is. All right. All of it's in your book. Let's see what else is here. All right. Now, in chapter 19, another important chapter. This chapter is sort of the preliminary information that you need to do StatQ, both confidence intervals and hypothesis tests. So this has to do with samples, diversity of samples. And actually, what I want to do is go to you guys here. All right. And give me a second here. I want to go to chapter 19 in the ebook. That's what I'm going to do next. All right, chapter 19. In the ebook, it's in part 4. And go to that. All right, so what I'm going to do is go through the topics that you should pay attention to in chapter 19. But one of the things they do talk about is this idea of inference. Inference meaning going from the sample, getting sample information and saying something about the population. That's what we do for confidence intervals, because we're taking the sample mean or sample proportion, and we're estimating the population mean or population proportion. So we're moving from the sample to the population. And we do that with hypothesis tests too. Because with a hypothesis test, we have some hypotheses about the population, and we're using the sample to determine if those hypotheses are true, or if there's enough information to support one hypothesis over another one. Okay. A second here. All right. So let's actually go back to the first page here. So that's what they're talking about here in this first page. We also know that if everyone in this class took a different sample of the same size from the population, we would all get different sample means, sample proportions, and that's called sampling variability. That's what they mean by dissimilarity among samples. That means there's the different samples would get different sample means and sample proportions, and that's why we have confidence intervals, for example. We don't use just the sample mean to estimate the population mean. We want to use some sort of interval of values to estimate the population mean or population proportion, whatever we're estimating. All right. So in this section here, they talk about proportions, percentages, and probabilities. Okay. Okay. And let's just move ahead here. I want to go to where there's some information that would be useful. Now, you all know what a proportion is. I hope by now you know what a proportion is, right? We have a category, and we're counting the number of people or things in that category. And the proportion would be the number that we count that have a certain characteristic divided by all the people that we're looking at. Right? That makes sense? So if we have a survey of 100 people, and we're asking them, do you like candidate A? And the answer is either going to be yes or no. And let's say out of the 100 people, 60 of them say yes, then the proportion would be 60 out of 100, or 0.6. That would be the proportion of all the people that we asked that question to who said they like candidate A. So I hope by now that you know what a proportion is, because That's really important to be able to know that. All right, otherwise it's going to be very hard to make interpretations about proportions if you don't know what a proportion is. All right, any questions about proportions and what they mean? All right. You know, here, and what they're showing in this example here is sampling variability, that for different samples, you're going to get different sample proportions. That's what this example is showing here. All right, the sample size is 25, and you're asking them how many people have a certain gene. And in one sample, 12 out of 25 have the gene. So when you divide those two numbers, you get 0.48. Another sample, you get 9 out of 25 people have that gene. 9 divided by 25 is 0.36, like that. All right, you can see all the sample means are different. So those are all point estimates. We call them point estimates of the population proportion. Population proportion is typically unknown. That's why we do the samples. So we hope that our particular estimate is close to that population proportion, but it might not be. So the question is, what would be a better way of estimating? And again, you do these things called confidence intervals. That's the whole idea. All right, bootstrap confidence intervals. Now, the rule for sample proportions. Now, these rules that are in this chapter here, you need to know. And let's read through what the rules are and the conditions for them. Let me just check one thing here before I do. Yep, let's see. So the rule for sample proportions. The following 3 conditions must be met for the rule of sample proportions to apply. All right, so we have to figure out what this rule is first. Number 1, there exists an actual population with a fixed proportion who have a certain trait, opinion, disease, or so on. That sort of makes sense, right? If you're going to come up with a sample proportion, it would make sense that the actual population also has that proportion for a trait, opinion, or disease that we're looking at. Or there's some sort of thing that we can repeat over and over again where we can come up with this proportion using the relative frequency approach to probability. The second one is a random sample selected. That's important. Without random samples, we can't use probability. So that's another requirement, is a random sample needs to be selected. Now, on your final exam, sometimes they'll ask assumptions that can be used for confidence intervals, that could be used for hypothesis tests. This is always one of the assumptions, right? You always mention this when they ask for assumptions, a random sample. You'll always get points for that if you say that. So you might want to write that down. And they ask for assumptions, for confidence intervals, for hypothesis tests. One of the assumptions is always that the sample was selected randomly. We have a random sample. All right. Another requirement is that the size of the sample is relatively large. All right. Now they don't tell you how large, but they do tell you it should be large enough. So that's another requirement for this. All right. They give you some examples here, but these aren't really that useful. So I'll leave it over with you. All right. Now, one of the things that's required for this rule for sample proportions is that we calculate what's called the standard deviation for a frequency curve. And the frequency curve is what? It's a curve that is made up of different types of proportions for various samples that we could possibly get. In other words, if 1,000 people did a random sample, did the same type of random sample, the same number of people were being asked and being asked the same thing, you would all get different sample proportions. If we listed all of them and did a curve, let's say we listed all of them in some sort of graph, like a histogram, and we did a curve, we would come up with a frequency curve. It would look bell-shaped, probably. And the standard deviation of this curve is this formula here. It's the square root of the true proportion times the 1 minus the true proportion divided by the sample size. Let's just look at an example of this right here. This is something that you should know. So suppose of all voters in the US, 40% are in favor of candidate X. So this is something that is, this is a hypothesis. We would call this a hypothesis, all right? We don't know this for sure, but we're hypothesizing this. Now, suppose pollsters are all taking samples of 2,400 people. So let's say there's 1,000 pollsters out there. Pollsters are people who do the sampling, right? And what proportion of the sample would be expected to favor candidate X? Okay, that would be one of the questions that we could ask if there were 2,400 people in a sample. Now we're guessing it's in the vicinity of 40%, but we don't know for any sample if it's going to be 40% or some percentage lower, some percentage higher. But we could calculate what's called the standard deviation of this frequency curve. And it's the square root of P of this proportion times 1 minus proportion divided by the sample size. And this is what it is right here. See, the proportion that's being hypothesized is 40% or 0.4. We don't put percentages in. We put for proportions, we use decimals. So it's 0.4 times 1 minus 0.4, which is 0.6, divided by 2,400. So if you put this all into your calculator, you get about 0.01 as your standard deviation. Now they say 0.01 is 1 out of 100 or 1%. So that would be the average spread of this frequency curve. All right, the standard deviation of this frequency curve would be 0.01. Now, here's the big deal about that. Why do we need to even calculate that? Well, if we wanted to see the possible range of different sample proportions, in other words, again, we have 1,000 people maybe who are doing the same samples. We want to know what's the possible range of these sample proportions. Well, the way to do this is if we know we have the idea of what the population proportion is, in this case 0.4, and we've calculated from that the standard deviation, we know from this rule called the empirical rule that 68% of the sample proportions will be between 0.39 and 0.41. Now, how did we get that? Well, since the standard deviation is 0.01, and the empirical rule, which we had learned, I might have mentioned to you, says the following. It says that that 68%, if you have a bell-shaped curve, the middle 68% of all of the data will be within 1 standard deviation of the mean. Now, what's the mean in this case here? The average is 0.4. That's the population proportion. And the standard deviation is 0.01. So if we subtract 0.01 from 0.4, we get 0.39. And if we add 0.01 to 0.4, we get 0.41. And that's how they came up with 39% to 41%. It's between 0.39 and 0.41. We would expect 68% of the sample means to be between those two values. Or we would say there's a 68% chance that any particular sample proportion is going to be between those two numbers. And in addition to that, we would say 95% chance that the sample proportions will be between 0.38 and 0.42. Now, 95% is plus or minus 2 standard deviations from the mean. Remember? I hope you remember this. Right? This is an important thing right here. So this is, you tag this in your book, write it down. And how do we know it's between those two numbers? Because 2 standard deviations is 2 times 0.01, 0.02. You take 0.4 and subtract 0.02, we get 0.38. We take 0.4 and add 0.02, we get 0.42. And then it's almost certain that the sample proportion is between 0.37 and 0.43. Almost certain in this context means 99.7%. That's 3 standard deviations away. And again, if a standard deviation is worth 0.01, 3 of them are worth 0.03. We just multiply that by 0.01 times 3, it's 0.03. And if we add and subtract 0.03 from 0.4, we get 0.37 on the low end, we get 0.43 on the high end. That's between 37 and 43%. So if you see on your test a question similar to this, then this is where you go to look how to do it. You calculate the standard deviation first. You look right, and you calculate it because you have the hypothesized population proportion mentioned here. And then you use this formula to come up with the standard deviation, and then you figure out these percentages here. 68%, the range for 68%, the range for 95%, and the range for 99.7%. Okay? Any questions about that? It's not hard to do, but again, you need to remember how to do it. This is the rule for sample proportions. All right? All right. See how we're doing with time. I think we only have 5 minutes left, so I do want to pay attention on this particular topic here. All right. There's something similar for sample means. There's a rule for sample means also. All right. So when we deal with means, we're dealing with measurements, things that we measure, such as weight, all right, as opposed to counting things, as we do with proportions. And there is a rule for sample means. Okay. Now the rule for sample means, again, let's read through this. Again, this is in this chapter 19, so I want you to pay attention to this also. The population of measurements of the interest is bell-shaped, and a random sample of any size is measured. All right. So here's the random sample again. Population of measurements is bell-shaped. That's what's required to use this rule. And it says here, if the population of measurements is not bell-shaped, then we need a large random sample, and typically 30 or more is considered large. Now, I want to make sure that you understand what it's saying here. This is very important for the test. If you know that the population of measurements, the population that you're measuring, is bell-shaped, then it doesn't matter how large the sample is. Okay, the sample is below 30, it's okay, as long as the population is bell-shaped. However, if the population is not bell-shaped, if we're not sure, even if it's bell-shaped, then we need at least 30 as the sample size. If we don't have 30 as the sample size, okay, then we can't use the rule for sample means. Okay, does that make sense? So if the population is not bell-shaped, or there's nothing said about it, so we have to assume it's not bell-shaped, then the sample size must be at least 30 to use this rule. I'm mentioning this because this is something that could show up on your test, not in these words, by the way, all right, but it could be a scenario that is asking you to look at this, all right? So make sure that you have access to, that you look at chapter 19 very carefully. All right, that's my point. All right. And now let's look at the standard deviation used for means. It is the population standard deviation divided by the square root of the sample size. So this is a different formula for the frequency curve, the standard deviation of the frequency curve when we're dealing with means. All right. The rule for proportions has a different standard deviation formula. This one is the population standard deviation divided by the square root of the sample size. For example, here, let's look at this example, and then this might be it in terms of giving you a review. But again, I wanted you to know this. All right. So it says here, here's a weight loss example. The population mean and standard deviation were 8 pounds and 5 pounds respectively. That means the mean is 8 pounds. Standard deviation is 5 pounds. We took a random sample of 25. All right. Now, one of the things that you have to know here, obviously, is because the sample size is below 30, all right, they better mention that the population is bell-shaped, It has to be bell-shaped, all right, for you to use this rule that they're talking about here. All right. So, question is, for this bell-shaped curve that you're going to be using, what's the mean? Well, the mean is going to be equal to the population mean of 8. So we're good with that. The means are going to match. But the standard deviation is going to be the standard deviation of the population divided by the square root of the sample size. So it's 5 divided by the square root of 25, which is equal to 5 divided by 5, because the square root of 25 is 5, and is equal to 1. That's how they came up with 1 here. Okay? And therefore, if we want to know the different ranges of possible sample means, given that the population mean is 8, we would say there's a 68% chance the sample mean that we select will be between 7 and 9. Why? Because the population mean is 8, all right, and the standard deviation is 1, all right? So 8 minus 1 is 7, 8 plus 1 is 9. 95% the sample mean will be between 6 and 10. Why? Because 95% is plus or minus 2 standard deviations. In this case, the standard deviation is 1. 2 times 1 is 2. 8 minus 2 is 6. 8 plus 2 is 10. And the same thing almost certain means 3 standard deviations. Again, 3 times 1 is 3. And it doesn't always have to be 1, by the way, the standard deviation when you calculate it. It's just in these examples it is. All right. And that's where they got 5 and 11 here, because 1 times 3 is 3, and then 8 minus 3 is 5, 8 plus 3 is 11. All right, well, I'm running a little bit late, 1 minute late, so that is it for the review. I wanted to review those 3 chapters with you. Any questions about what I reviewed? So the reason I reviewed is because there's a good chance it's going to show up on your test. All right, that's why I'm doing it.
So when you was saying the ebook, you mean that's
The ebook. The ebook is your book online.
I don't have a book online.
Then you don't have an ebook. You have a paper book.
Right. That's okay. That's what I'm clarifying. I got the regular book.
Some
Okay.
people have ebooks, some people don't.
Okay, I got you.
All right. All right. Anyway, take a look to see if you see the quiz. So, quiz number 9. Give me a thumbs up if you see it. Yes? Okay, good. Great. You may begin. And again, this is a little bit longer, like the last one, 30 minutes, but many of you will get done well before 30 minutes. All right. It's a pleasure teaching you this semester. I don't know if I'll get a chance to say that. And good luck again today. Good luck on Thursday, which is the test number 3. Remember, we'll start at 8:05, 70 minutes long. And then next Tuesday, the following Tuesday, a week from today, is your final exam from 8 a.m. to 10 a.m. Please don't be late for that. That will also start at 8:05. We'll have about 2 hours. Most of you will get them well before 2 hours. All right.